All right, so let me just switch here. All right, you would have had your solution. So what we have on screen here, you would already have had. Nonetheless, I'm just putting it back here for what it's worth. Okay. So we have here a nice little circuit, three-mesh circuit. Now you're given node voltages, you're given mesh currents, which means that the choice in terms of how you approach the question will be totally up to you. All right. So you could either use mesh analysis or nodal analysis. Of course, parts 1 and 2 of the question forces you to form both the impedance and admittance matrices. All right, so notwithstanding the method that you're going to be using, you will still need to look at both matrices. So let's see what this. Just a minute, trying to find my pen. All right. Well, maybe I should first ask if there's anyone who had a difficulty with this particular question, rather than us just delving into it and solving. Did anyone have a difficulty in solving?
Yes, sir.
Yes?
Yes, sir.
Okay. All right. So first thing we want to do is to form the matrices. So for our impedance matrix, which is what part 1 I'd ask you to determine. So let's do that. All right. So for my matrix, within mesh 1, we have Z1 and Z2. All right. So it's simply add them. All right. So we have here 4 plus J5, and we have 7 minus J6. So we have 4 plus J5. We're adding that to 7 minus
multiplication.
J6. All right? So that's for that mesh. And if I do all the leading diagonal elements, here we have 7 minus J6, we have here 6, and up here we have 2 plus J9. So for the middle element, we have 7 minus J6, we have 2 plus J9, and plus, and we have 6. All right, and then for the third mesh, we have 5 minus J8, and we have 6. All right. So we have 5 minus J8. We're adding that to 6. So those are our leading diagonal elements. And then we can now put in the off diagonal. So between mesh 1 and 2, we have 7 minus J6. So we'll have here minus 7 plus J6, which means that if it's between 1 and 2, then it's the same between 2 and 1. So that is minus 7 plus J6. There is nothing linking meshes 1 and 3. All right. So it means that the impedance there it's really not zero, but anyway, it's really infinity. But then we're not going to stress on that. And then between mesh 2 and 3, we have 6. All right, so it means that we'll have here minus 6, minus 6. All right. So the simplified matrix would be 11 minus J1 or minus J, minus 7 plus 6, 0, 0, minus 7 plus J6. And in the middle, we have here 15 plus J3. Then we have minus 6, and 11 minus J8. So those are our impedances. For the voltages, all right, so we go back. For mesh 1, all right, we'd have the negative of 25 at angle 30, and also the negative of 18 and 45, because of course we're going in this direction, yeah? Which means that we'll be coming down. So we have here minus 25 at angle 30, minus 18 at 45. All right. And here for mesh 2, we'd have 20, we're going into the negative, and plus 18. So that's 20 at 60 plus 18 at 45. And then for mesh 3, we would have minus 20 at 60. All right, so this is what we will be solving. All right, for I1, 2, and 3. Any questions? I didn't see who said that they didn't understand it. Do you have any question with this section, with this so far?
No, sir. I have that exact answer.
Okay. All right. Now, the question asked for the impedance values at position A22 and A21. All right. So what we're asking for, A22 would be that. Yes. And A21 would be that. Okay. Now, what we have here are the complex representations. So, of course, you would have to convert that to polar. Right? So, whatever the polar values are for these, I don't have the values before me, but whatever the polar values are, then that's what you would use. Those would be the impedances. Based on what? Based on these values, we're talking about 15, right? Just over 15. But whatever they work out, that's what we're asking. For now I know that well, at least one individual, I think I looked at well, in looking at their solution, I asked for the admittance values. Yes. Now, the circuit that we gave you have V1 and V2, yeah? So it means for the admittance matrix, what we are asking for. So you'd have your 1 upon 4 plus J5, 1 over 2 plus J9, 1 over 7 minus J6. And then you'd have minus 1 over 2 plus J9, minus 1 over 2 plus J9. And here you'd have 1 over 6 plus 1 over 5 minus J8 plus 1 over 2 plus J9. All right. And you're multiplying this by V1, V2. And this is equal to 25 minus 25 at angle 30 over 4 plus J5 plus 18 at 45 over 7 minus J6. And down here we'll have minus 20 at 60 over 6. All right. And you solve that for V1 and V2. All right. So those are your matrices. From there you solve, you get your V1. Where V1, well, I'm not looking at the values. I think V1 works out to 22 at 171 and V2 7.7 at minus 60. I think those were the values. Right? I'm not looking at them. Anyway, once you have had V1 and V2, going back to the circuit, once you have had V1 and V2, then the rest, you're asked for the current through impedance Z2. All right, so you're asked for the current through this. So you have two options. You could divide V1 minus 18 over 7 minus J6, and that would give you this current, yes? So that would be IZ2. So that's one option. Or if you had used the mesh analysis, it would be I1 minus I2, all right? And you're looking at the current flowing down. The other one, Z4, the current through Z4. Again, it is V2 plus 20 angle 60 over 6. Or if you use mesh analysis, it's I2 minus I3. For the total active power supplied to the network, well, since you had calculated the currents through these impedances, through these two impedances, yes, it means that you also know the current for these sources. And based on the direction of flow. So if you calculated the current through Z2 going in this direction, it means that it would be entering the positive side or the line side of this source, which means therefore that this source in delivering current, it will be delivering the negative of whatever value you had calculated. So if the current, let us say the current was A plus JB. Let's say that's the current which is going in this direction. It means therefore that the current you'd be using would be minus A minus JB. However, because you're looking at the conjugate, then it will be minus A plus JB. So that's the current that you would multiply your source by. For this one, it would be 20 at angle 60, yes, times the current, times the conjugate of the current going through there. And over here, it's minus I1, or the negative, or the conjugate of the negative of I1 times the 25, okay? And if you have the time and you want to confirm, then you would multiply the modulus of the currents through each branch by the resistance, the corresponding resistance, and add them. Both should be equal. So you would have gotten S, the currents, the powers rather, for the sources. You'd simply add the active parts. Right? And that would give you your PT. Yep, and that's it for question 1. Any questions?
Sir,
Yes.
in terms of knowing whether they're positive or negative, should we always assume that up is positive? That up is negative? Or
For what?
for the power sources, sir.
No. You are about which positive versus negative. Is it you mean with respect to the current?
No, sir. The sources, sir.
All right. The source, all the source tells you, you know, the arrow here tells you which is the line side, okay? Or for use of a better word, which is the positive side. So let's say that's the positive side. Not let's say, but this is the positive side, okay? As it relates to the sources. Now, when you're considering the current being delivered by the sources, if the current, for example, in this instance where I1 would be the current through the 25 volt source, you agree with that? I1 is flowing through that source.
Yes, sir.
The current is actually going into the positive of the source. So, in effect, if using I1 going into the positive, we are saying that this current would be charging the source. I know we're dealing with AC, but we'd be saying that it's charging the source, or the source is absorbing power. However, if we're looking at delivery, it means that we're looking at the current going this direction. So it means that the negative of I1 would be leaving the source. So if I1 was equal to A, as I just said, A plus JB, then the negative of I1 would be equal to minus A minus JB. However, S, regardless of what is happening, S for the source is calculated as this. So although I'm looking at the negative of the current because I'm looking at the supply, I'm delivering power to the network, the conjugate would now be A plus minus A plus JB. All right, so it's just that I'm looking from the perspective of the source supplying power.
Sir,
Mm-hmm.
if it is that you just invert the impedance to get the admittance, would that be the same thing, right?
You mean if I had just found this, the inverse of this?
Correct.
Huh?
Yes.
Okay, so let us use that. Let's use that reasoning. If I inverted this to get the admittance matrix, yeah, what would I be multiplying it by? Which voltages?
Can you repeat that, please?
I'm saying if I'm using the admittance, because we would have IV equals, what am I saying? Yes, I'm sorry. Let me just correct this. I'll be saying YV is equal to I. Okay? Agreed?
Yes.
All right. So I want you to give me the voltage matrix. What are the voltages? What are the node voltages that I'll be multiplying by? If the admittance, based on the question I asked, if the admittance matrix was what we have there. Do you agree that the inverse of this would be at 3 by 3? Hmm?
Yes, sir.
Okay. So I'm still asking the question, what would be the voltage matrix? Hmm? Do you understand the man, was it Miss Ellis that just asked the question?
Yes, sir.
So do you recognize the conundrum that you have here? You see the impedance matrix, the impedance matrix is formed based on the mesh currents. The admittance matrix is formed with relative to the node voltages.
Okay, so basically we had to do mesh and nodal.
In order to determine the elements. So I wasn't asking you to use mesh and nodal to solve the problem. What I wanted from you, what I wanted to ensure is that you can form both the admittance matrix and the impedance matrix based on the two methods. So the short answer to your question, Lamanja, the short answer to your question is that this would be wrong. Right, because this is referenced to the mesh currents. This is referenced to the node voltages. All right? Then power system is going to tell us something completely different, but let's wait until we get there. All right? Any other questions?
Question. Let's say for the Z2, you did the current based on the direction of the source, and you did the I2 minus I1 because I used the mesh analysis.
Mm-hmm.
Would that still be correct, sir?
Yeah, well, if you did I2 minus I1, right? Then what you are looking at is the current going in this direction.
Correct.
Agree? You agree with that?
Yes, sir.
Yeah. Now if you're looking at the current going in that direction, then S, and let us call this current IZ2, all right? Then S would be equal to 18 at 45 times the modulus of IZ2. You agree with that?
Yes, sir.
All right. Now, isn't this equal to the negative of I1 minus I2?
Yes, sir.
And isn't I1 minus I2 going in that direction?
Yes, sir.
So it really doesn't matter.
Sir, to sum it up then, when the current is entering the source, you change the sign base, so you make it negative.
Folks, to sum it up, it's the same thing that we talked about in Networks 1. About supply of power, absorbing power. We said that it is supplying when the current is leaving the positive, no sir?
Positive side.
Yeah. We have not changed anything, all we have done is to migrate from resistive only networks to putting in some inductance and capacitance. We have not, those principles remain. I have not changed, well, I can't change any of them. Those principles must hold up. All right? So don't make it more complex than it already is. Let's just keep it simple. Okay. All right, so let's talk about question 2. Or well, any other questions with this one? Anybody? All right, question 2. So we know we need to redraw. And we are removing our load, so we have an open circuit. Any suggestions? Let me hear the approach you would want to take. And based on what we saw coming out of the test, I'm not going to continue giving you the benefit of remaining quiet. So let me go down the list. So Campbell.
Yes, sir.
Conroy?
Yes, sir.
All right. Approach.
All right, so we open the load, short circuit the sources, and take resistance looking from the load.
What are you finding out there?
Hold on, I don't have the circuit. I don't have the circuit, sir.
I'm not hearing you.
I don't have the circuit. Let me just draw the circuit. Can I bring?
I want to know what you're finding. You just started telling me to this, that, and that.
So we can find R Thevenin by opening the load.
We're going to talk differently because if you look at the circuit, you have inductors and capacitors, right?
Yes,
what
sir.
you're finding is Z Thevenin.
Oh, okay. All right. Yeah. Oh, so okay. So we open the load and find Z Thevenin looking from the load side.
All right. What does
and-
that work out to?
So that would be the 6 minus 8J in parallel with the other side of the circuit. I haven't worked out the actual number.
All right. So you have the circuit.
Hold on, sir. Let me finish rejoin.
Why are you drawing it? Didn't you do do it from the test?
Yes, sir, but I don't know where I put the papers. Hold on, sir. Give me a minute, sir.
All right. Well, while it takes a minute, let's see who Sir Clark, Marcel.
Yes, Chief.
Come on, come now. You wanna give me the impedance equation?
Repeat that, sir.
The equation, the impedance equation. Or give me the expression to find the total, the impedance looking into the open circuited terminals.
Find out in the paper, you know.
Yeah, leave the paper, man. Let's look at it. Conroy, are you back?
Yes, sir.
All right, go ahead now. So let's look at the circuit and give me the expression.
In our class, here, Arnold.
Go ahead. All right. Can I get a volunteer?
Sir.
Yes, sir.
Right. Huh?
You can either start with the VTH or the IN.
No, just give me the expression. Since you had already started with Z Thevenin, just give me the expression for Z Thevenin.
Z 6 minus 8J parallel.
6 minus 8.
J parallel.
That's 6
open
minus.
bracket. Open bracket. 7 plus 9J. Plus open bracket. 6 minus 5J. Parallel to 9 plus 12J.
Okay. All right. And of course, I know we are all experts. So we solve that. Whatever it worked out to, we do that. We do that. And the value, it comes 3 minus J 3.155. So that is your Thevenin. Your Thevenin impedance. All right. So let's go back now to our circuit. What method are you planning to use?
Mesh.
Mesh, sir.
Mesh. Why do you want to use mesh?
Easier to find the impedance matrix.
Huh?
Easier to find the impedance matrix.
If you say so.
Less confusion, sir.
Less confusion.
Yeah.
All right. Okay. That's very dangerous, though. So, this is mesh one. This is mesh two. All right. Was that your selection?
Yes, sir.
Right,
Yes,
cool.
sir.
All right. So, what's the? Give me the mesh equation.
19 minus 4j.
19 minus J4.
Minus 6 plus 5j. Same thing, minus 6 plus 5j. 15 plus 7j.
Okay.
I1
I1 and I2
equal 50 angle 30. 100 angle minus 60.
Okay. All right. What you got for I1 and I2 now?
I1 was 1.0714 and
1.0714.
0714.
That's it?
Angle minus 38.769.
Okay. Well, I suppose we don't need I2, right?
Correct.
Okay, so what's V Thevenin?
50 angle 30 minus
07.
minus 6 minus
Minus
minus open bracket 6 minus 8j multiplied by I1.
Okay, no, very good.
56.3999.
All right. So we can call it 4, right?
Yeah, angle 39.281.
56.4 at an angle of
39.281.
all right. I'm just curious. I mean, you're perfectly correct, but I am curious. Did anybody use know that?
Yes, sir.
And you got the same value, right?
Yes, sir.
And you got it in one go, right?
Yeah, one go.
Yeah. Yeah. Huh? I mean, it is totally your choice, but if you made this node 1 and this node 2, instead of finding in using mesh, you find I1 and then you use the 50 minus that. If you use V1 and V2, once you find V1, then that is V Thevenin. And you're done. But to each his own. I'm not going to try and get you to think like me. All right, so we have the Thevenin voltage. All right. We wanted the corresponding Norton current. So of course, I Norton would have been equal to E Thevenin divided by Z Thevenin. Okay. That was 7.6 0.90923 at an angle of 62.57. Right? Amperes. All right. Now, the next part of the question is where I think several persons may not have really understood what was being asked. And, you know, all right. So, the question asks, the active power supplied to the circuit. Now, your Thevenin circuit, that would have been your supply. This would have been your impedance. Now, and this is your load. Now, what are we told about the load? What's the condition for this?
Both the resistance and the load resistance equal the same.
The load equal the load equal the Thevenin resistance.
Yes?
The quick question, sir. How you have for I naught is equal to E Thevenin over R Thevenin? Isn't it E Thevenin over 2 R Thevenin?
Well, this is the formula, you know.
Sir, I have a question to answer that.
Go ahead.
I can go back on the diagram. Let me show you. If in the scenario that you had worked out IN first, which you'd have replaced the load with a short circuit, and you would have done your mesh, and you'd have found your I1, I2, I3. It's supposed to come out back to the exact thing, or the principle in itself would be correct.
Yeah. Anyone you want to find first is up to you.
Oh.
All right. You get the same I naught that we have. And then, of course, we know that Z Thevenin and Z naught are the same, right?
Yes, sir. I think some of these issues are calculator issue and not concept issues.
Okay. So, since we are talking about to the circuit, what we have is what this represents is the equivalent circuit at the load point. You with me? So beyond this load, outside of that load, this is what the circuit is reduced to. So when I add the load, it means that this voltage would be supplying that total load. So the power we're talking about would be the power supplied to 2 times Z Thevenin.
Oh yeah, that's very good. Yeah.
All right?
Go over that again, sir.
I'm saying your Thevenin equivalent would have been this. You agree?
Yes, sir.
All right. So in other words, what you have is at this point, outside of this load, everything in the circuit is reduced to these 2. That's the equivalent circuit at those terminals. So when you add this, the total impedance in the circuit will now be 2Z Thevenin. Okay?
Because maximum power.
Which means that the supply will be supplying that total impedance. Similarly, for part D, for part D, The power by the load would be, well, whatever we just be considering this. So we'd find IT, yes, and then IT would be passing through your it means that IT would be passing through your load. Good. So the energy, you'd have the power. Yes. And then you would find E. And you're looking at the active power, huh? It's a P you're looking at. All right. I don't think many persons had an issue with this one. So let's look at question 3. So image impedance. Ms. Lynch.
Sir.
Help me out now. We'll find image impedance.
So you have to look at the open circuits at both ports. The open circuit and the short circuit. So if you look at the open circuit, looking from port 2, you will get.
So you're dealing with port 2 first, all right?
You will get 10 in parallel with 6 plus 8.
Okay.
And looking at the same port for the short circuit, you will get 10 in parallel with 8 plus 6 in parallel with 4.
Okay.
And to find the image impedance, it will be the square root of the open circuit multiplied by the short circuit.
Everybody comfortable with that?
Yeah. Yes, sir.
Okay. Thank you, Ms. Lynch. So for this one, when you multiply those and find the square root, you get 5.453. All right? And for on this side, yes, you go through the same process. You get 7.946. All right, no, Mr. Grant.
Yes, sir.
Section, well, that's supposed to be 4. Section 4 there. I'm not asking you to calculate the energy. But we said that the circuit is supplied
with 40.
With a 3 amp source. Section, the fourth section. I see that the 3 is repeated, but that should be section 4.
Oh, okay.
So we want the energy consumed in 2 minutes by the network if a 3 amp source is connected to port 2 while terminated in its image impedance. So if I have the source at port 2, yes?
Yes, sir.
Okay. What would be the impedance experienced or seen by that source?
Impedance seen by the source.
So here is my source. I have 3 amps here.
Yes, sir. We'll have the impedance would be the 10 in on the 8s, 10 in parallel with the 8s and 6. Well,
So I'm terminated in the image impedance. So what impedance am I seeing? All right, let me ask you. What I'm really asking is for you to use the definition for image impedance. All right, let's start with the easier one. Maybe I should have done that. Let's deal with the easier one. The part 3. If I put the 40-volt source at port 1, when the network is terminated in its iterative impedance.
yes, sir.
All right. What impedance would I be experiencing?
The 5.453.
Oh, but that has to do with, you know, I'm being harsh. I'm being tough. So let us work out the iterative impedance. Maybe I should do that first, right? It's not 4.5, 5.453. That's not it. So let me do the iterative impedance first. We're coming back to you now, Mr. Grant.
Not a problem, sir.
Let me see who else is out there. Wide. Miss Downer.
Hi, sir.
How you do?
Not bad, sir.
That's excellent. All right, so we want to find the iterative impedance. So what do I do?
Sorry, so so the first thing I would do is,
Tell me what you did.
sir, I actually didn't do that question.
Oh, you didn't do it. Okay, all right. All right, so tell me what you do.
So I'm not really sure.
All right, fair enough. So first with us, Forrester with us. So Forrester?
Sir, I'm here, sir. Just pull over. Give me a minute. I'm pulling out the notes, sir. The iterative impedance support 1 and 2, sir.
What you can't be driving and in class, Mr. Forrester?
Sir, I'm always coming from country, sir. It's the unfortunate truth. Most times my days end at 6 and 7.
You're a busy man. All right.
Not busy,
I'm
sir.
not going to be the reason for you doing that. So drive and listen. I won't quiz you on this one. Mr. Merritt? Mr. Merritt? Front and center. Where? Go ahead, Mr. Merritt. I cannot hear you though.
Yes, sir.
Tell me where Mr.
I'm here, sir.
Yeah, man, we figure that, but I needed to tell me what to do.
Sir. All right, sir. What we use the power use PX and
the what? You heard the question? It's part 2 we're doing it.
Oh, part. Oh, sorry, sir. All right, sir. From looking into port 1, we use the ZOA, which was 7.946, and put it at port 2, and then look inside the circuit, find the impedance looking inside from port 1.
All right. We're trying to find the iterative impedance.
Yes, sir.
That's not the correct approach, Mr. Ms. Phillips?
Yes, sir.
Yeah, man. Mr. Merritt needs your assistance.
Sir, I just come off the road, sir. I just joined the class.
What is this? Porter. We need you. Oh, you just come off the road too? Oh, okay. Yeah. But how do you know what? Define iterative impedance, sorry.
So the impedance that when you're looking in from either port, it's equal to the
impedance measured on the other port. So it would have been, for example, it would be the impedance that when port 2 is connected to the other, when looking at one port, it will be reflected at the other port.
You think you're gonna get that right past school challenge, Mr. Wilson? I have no clue what that means. Folks, this is what we have, you know.
Oh, sir. So, sir, it will be the impedance that when connected to one port, when you measure the impedance at the other port, you're supposed to get the same value. So that's will be the same.
Which is what I just drew, right?
Yes, sir.
Good. So it means, therefore, that you would have to form the impedance equation. So it would be that ZA. So once you put that in, since we're dealing with port 1, all right, just for clarity, I'll put in Z1.
And Z2.
All right, so this would be Z1 when I connect Z1 there. Yeah. So it means, therefore, that Z1 is equal to 4 in series with 6 in parallel.
With 8 in series with 10 in parallel with the 5.4.
In parallel with what?
The image impedance, which was 5.4.
No!
Parallel with Z is or Z1.
Parallel with Z1.
Yes, sorry. Yes.
And you solve that.
I'll find Z1. Mm-hmm.
When you solve that, Z1 is 8.05. So now I am understanding why so many persons got the first part right, but couldn't figure out the rest.
Sir.
Yes.
That's what I had, sir. But that maybe it's the way I explained it wasn't right, sir. But that's what
Who is
I
that? Merit?
Yes, sir. That's what I got.
It's not Merit.
Yes, sir.
You know my response to that, right?
All right, sir. That's the word.
Okay. The best engineering design is of no value. We can explain it. All right? Similarly, if you make that Z2, when you look inside here, you'll see Z2.
With 10 in
Right.
parallel 8.
So Z2
with 10 in parallel with 8. Can't see circuit.
Huh?
Yeah, in series with 6, in parallel with 4, in series with Z2. Series with Z2.
Right? And here Z2 is equal to 5.38. All right? So now, once you have done these, then the other parts of the question become very simple. All right? Oops. When we know so the power supplied by a 40-volt source connected to port 1. If I put in my source connected to port 1, that's my 40 volts. And we are saying that it is terminated in its iterated impedance. It means that this would be Z1. Okay? So the power supplied would be 40 squared over Z1.
Mm-hmm.
Are you comfortable with that?
Yes, sir.
Yeah, why is 40 squared over Z1, sir? On to the rest of the circuit.
Miss Gray? You're here? Miss Gray?
Yes, sir.
Explain that to Mr. Adams for me, please.
Yeah, because it's terminated in the iterated impedance. So basically, sir, Z1 would represent all of the total impedance in the circuit.
Thank you very much. You get that, Mr. Adams?
Yes, sir.
Good. So the theory, it's not just about, throwing around numbers. You have to understand the theory. All right. The other section now, because we are dealing with the image impedance, we are told that the 3 amp source is connected to port 2. All right. So, Mr. Grant, I'm back with you now.
Yes, sir.
Mm-hmm. So that 3 amp source, what impedance will it be seeing? You're there? So Grant, disappear?
That's a 3 and squared. Sir, you hearing me?
Yeah, man, I'm hearing you now.
Okay.
So that?
Yes, sir.
Yeah.
You change out the 2 minutes.
Forget about that part, man. That part, all right. I'm asking you about the impedance.
The impedance?
How would you define image impedance? If I terminate it in its image impedance, what impedance would I be seeing?
Image impedance. It will be seen for 2.
You know, did anybody get this correct? All right, there's silence. Do me a favor, folks. I need to put up question number 4. What I want you to do, you calculated the image impedance of port 2 to be 5.453. Yes? And you calculated the image impedance at port 1 to be 7.946. Terminate the network in its image impedance and work out the total impedance going towards the source for me, please. While you do that, I will upload question 4. Okay. Ready for me now, Mr. Grant? Where's Mr. Grant? Mr. Crossdale.
Yes, sir.
All right, help us out.
All right, sir. So to terminate port 1 using 5 to 5.453.
But why would you do that?
Sir, so they use the image impedance of port 2.
All right. Let's start with image impedance again. If I terminate port 1 with the 7.9, what's the impedance I see at port 2? Let's work it out. All right, come folks, work with me. Work with me. Let's just do a rough. I'm going to do a very rough calculation. So 7.95. All right. So if I put 7.95, sorry about that. If I put 7.95 here, I'll call it 8. Let's call this 8. Just for the purpose of doing a very quick calculation. 8 plus 4 give us what? 12.
So you want the answer, sir?
12 in parallel with 6.
5 points.
12 in parallel with 6 give us what?
4.
4. 4 plus 8.
12.
12 in parallel with 10 is about half of that, right? Half of 10. So it's about 5 point something. Agreed?
5.45, sir.
5.3854.
All right. So about that. Good. Get the gist? So if it's terminated in its image impedance, it means that we'd have the 7 over here. So it means that the 5.453 that we got would be what the 3 amp source is seeing.
Oh. So that you find the power and then multiply by the 120 minutes.
Yes. I keep saying it, and it's just my way of testing and retesting to ensure that you understand what we're doing. So I'm not going to be asking you for definitions. But I make you apply it just to make sure that we all understand what is happening. Okay, folks?
All right, sir. So just for clarity, sir, could you go over, not just don't work it out. I just wanted to tell me what does it mean by terminated in iterative impedance and image impedance?
All right, do me a favor. Tell me what it says in the notes that you have taken. Define this for me. From your notes. Yeah, man.
Give me
No
a second.
problem. No problem. No problem. That's what we are here for.
All right, sir. For iterative impedance, it says the iterative impedance is the value of impedance which, when connected to one of the 2 ports, produce an impedance the same value.
All right. So, as we said, if this is my network and I terminate it in its iterative impedance, if I come around here and measure the impedance, I'm going to get Zi. That's the definition. You with me?
Yes, sir.
So if it is terminated in its iterative impedance, and then I put a source here, yes, that source would only be seeing this impedance.
Yes, sir.
Right? With the image, right? Let's call that Z1 and that Z2. So for this port, for port 2 it's Z2, for port 1 it's Z1. If I terminate from port 2 the network in its image impedance, it means that I have terminated it in Z1, which means that it will give me the value Z2. If I'm at port 1 and the network is terminated in its image impedance, it means that it is terminated in Z2, and it will give me the Z1 value when I look in here.
Okay, sir. Thank you, sir.
You get the difference?
Yes, sir.
All right.
Close enough, but
Huh?
kind of tricky, but me kind of get it.
It's not tricky, man. But anyway. All right, so let us look at question 4. Question 4, there was an error. The parameters H just a sec. Let me get them.
All right, sir.
The parameters were 102/19, 2/19 minus 2/19 and 357/1938. All right. So those were the hybrid parameters. Now, what I didn't tell you is that these parameters were derived from a question that I had given you as an assignment, which means, therefore, you would have been familiar with it had you done the assignment. But anyway, that's water under the bridge. I don't think I need to go into the conversion. So what we want here, let's call that TB. All right? So we want H. I want to convert that to T. All right? If my memory serves me right, and that's a very tricky thing to depend on these days. But anyway, over H21 minus H, I remember that one.
H11.
It's 1 over 2 1. So this will be 2 2 over 2 1. And I think this was 1 over H21.
H21 should be minus as well.
The 2 2?
Yes, sir.
Okay. All right. So you convert delta H is equal to 1. All right. So with delta H equal 1, right away you are seeing that these two, you are seeing that it's a symmetrical network. But it may not be very obvious. So for T, this will be 9. This will just be the reciprocal of H21. So you would have here 19 over 2. This will be 19 over 2. This one worked out to 51, and this worked out to 1.75. All right, so that was your TB. That's for the network in the middle. For this, of course, you can take off this and that. Now, you would note that we have reversed the 3 and the 4. Yes, so once you have determined the transmission parameters, and let's call this network A, and that's network C. Once you have derived the transmission parameters for A, you automatically will have those for C, right? But you need to note that the 4 is here, and the 3 is here, over here the 3, and then 4. All right, so that's the only difference. So I'll just give you for TA. Does everyone have this? All right, so TA.
Okay, sir.
It's all right, I'll keep it. It was getting a little messy, but. So this was the transmission for A. The transmission for C, so TC, because of, you know what, let me not gear in a shortcut. When you find TC, it comes out to 15 over 6, 99 over 6, 1 over 6, and 9 over 6.
Sir.
Yes.
Is this circuit that the one that we did on the Friday and not the Monday?
Yes, the one you did on Friday.
Okay.
The one you did on Monday, I gave you a Pi network instead.
Sir, for the Friday one, no, the Monday one I got, yes, Pi network.
Yeah, I know. This is from Friday. All right, now once you have these, then you're doing T. And remember, it must be in the same order that the networks are connected. So it's TA, TB, TC. All right? Everybody have this?
Yes, sir.
And so T worked out to be 146.69. $1061.44 and 20.27. So you just substitute this into the equation. V1 is 10. So I'm not going to write the equations before I substitute. All right. So V1 is 10. So we have 10 is equal to, and then it would be A times V2. And V2, we know is equal to minus 10I2. Okay. So this would be 1466.9 I2 minus 1061.44 I2. Okay? And then I1 is equal to minus 202.7 I2 minus 146.69 I2. All right. And I think from this, everybody should be able to complete the solution. So the first equation, straight off the bat, you're able to calculate I2. From the second equation, the value you get from the first, you substitute, you get I1. So you now have V1 equal 10, you have I1, you have I2. 10 times I2 gives you V2. Or 10 times minus I2 gives you V2. All right? So you now have I2, which is the current flowing through the load. You have V1, you have I1. So you can find the power supplied to the network, energy consumed by the load. You already have that. Current flowing, which is I2. So that's that for the problem. I used the same network. So I use the same H parameters for what you got on Monday. But in changing the arrangement of the resistors, I gave you a pi network. So let me just see if I can superimpose it on this.
Sir, just a question before we move on to the pi network. For B in the first T network, sir, isn't it 9? I don't understand how you get 99/6.
Yes, sir. I was gonna ask the same question.
For B in the first T network, sir, got 9.
You got 9.
Yes, sir. And for D, I got 5/3.
Same, sir. Oh, okay. All right, let's see what we did wrong now. So we have them short circuited, right? Agreed?
Yes, sir.
So, whoa, where did I get this from? I have 6 in parallel with 9. Where did I get that from? Wait, 6 in parallel with 3. V1 over I2. So I have here 3 into a short circuited. So I have a 4. Oh my Lord, where did that come from? I'm looking at for V1. Just a minute. V2 short circuited. Am I looking at network A, right? That's great.
Sure.
Network A. All right, so if I short circuit that, I would have 6 in parallel with that's 24, that's 2.4. 24 over 10 plus 3. All right, let me just work this out. Pen. All right, let me go to the page. So we have here 3, 6, 4. All right, B is equal to V1 over I2 with V2 equals 0 or minus I2, sorry. Okay. So we would have V1, or we want V1 in terms, so it's 3. And over here we'd have 6 in parallel with 4, right? So this is 24 over 10. So this gives us 54. That's 54 over 10. And we are dividing that. We're dividing that now. So it's 54 over 10 times V1. All right, over 54 over 10 plus 3. Yes? So we have 54 over 10 V3. And we're dividing that by 10 over 84. So I have 54 V3 over 84. And we're dividing that by 4 in order to get times 1 over 4. Yes? So I have 54 V1 over 320. Right. So we're getting what's 336 of right? 4 is 32, 4, that's 320 plus 16. 336. All right, obviously I have made an error with this one.
Sir, aren't you looking for the voltage at the 4 ohm resistor? To get
which is the division that we have here. The division we have here.
You have 6 parallel 4 times V1 divided by 6 parallel 4 plus 3.
So the 6 parallel 4 is a 24 over 10.
Yes, sir. Times V1.
Right? So I am now, what did it, I look like I'm losing it today. I am losing it today.
Sir, I use a different method.
I'm coming to you.
Best of it, sir. So
I am losing it today. All right. So we're dividing by 3 and 24 over 10. I don't know why I put in the 54. So let me do that again. Over here, we have 6 times 4 over 10 to give us 24 over 10. So I'm dividing between 3 and 24 over 10. Okay?
Yes, sir.
So it is V1 times 24 over 10 divided by 3 plus 24 over 10.
Yes.
All right? So I have 24 V1 over 10 times 10 over 54. That's 30 plus 20, right? I get 24 V1 over 54. And I'm dividing, that would be the voltage across here. So I'm dividing that now by 4. So I get 6 over 54 V1 is equal to minus I2. So V1 over minus I2 is 54 over 6. That's 9. All right? That's what you're saying, right?
Yes.
Yes, sir.
Yeah. So there's an error there. So that would be 9. For D, I don't know where I got this 6 in parallel with 9. Anyway, for D, it would be I1 over minus I2. So I would have I1 here, and I'm finding the current through here. So it would be 6 I1 over
What is it?
10. Where did I? Oh, I worked this thing with 9. Anyway. And that's equal to minus I2. Okay? So I1 over minus I2 is 10 over 6. Should be 5 over 3. All right, so I will update this solution. I will correct this solution, and I'll upload it. I'll upload it to Schoology. Okay. So just draw a line through what I gave you earlier. I will correct it and upload it to Schoology. For the for the pi network that we had used, that I gave you on Monday. All right. For the pi network, you had here at 6, 4, I have 3. Okay, so we have your 6, 4, and 3. For A, we have V1 over V2. So we have V1 here, we have V2 here, we have I1, we have I2. So A is equal to V1 over V2 with I2 0. So V2 is equal to 3 V1 over 9. All right, because V1 would be seen across the 4. So it means that it's being divided between the 6 and the 3, all right, which are in series. So V1 over V2 is equal to 3. For C, we have I1 over V2. All right. So if I call, let me just get another color. If I call this IX, so I want the current going through the 3 ohm. IX is equal to before I1 over 13, all right, and V2 is equal to 3 IX. So we have 12 I1 over 13, which means therefore that C, which is I1 over V2, would be 13 over 12. If I now put on the short circuit, B, the V1 over minus I2, V2 being equal to 0. Yep. So of course, V1, because of the short circuit, it means that the 6 and the 4 will be in parallel. So V1 over 6 is equal to minus I2. All right. Or in other words, B is equal to 6. I'm just going to put D over here. D is equal to I1 minus I2. Okay. Again, with V2 equals 0, so we are maintaining the short circuit. So minus I2 would be equal to 4 I1 over 10. All right, which means that D is equal to 10 over 4. All right, so your matrix would be 3, 13 over 12, 6, and 10 over 4. All right. The same is true as with the previous example. So this would be my TA. For TC, right, we'd have 10 over 4, 3, 6, and 13 over 12. All right, because the network, these resistances would be interchanged. Remember I had indicated we use the same hybrid parameters. So they let me know when you have this. Don't have another slide, or if I could include it here. All right, so TB would remain as how is TB? 9.5. 51, 9.5. I mean 1.75. and this would be 9.5. All right, and then we have TA, TB, TC equal to T. All right. So T works out to 325, 864, 122.25, and 325. All right, so that's your network. That's your overall T. Again, you substitute into your equations, and you calculate the power. But you find your I2, your I1. You already have V1. You really don't need V2. All right, so I decided to go through these, and thank you, so what's none, Miss Gray, for that. For just pointing out that error. I'll correct it and upload, as I said. But I decided to go through this because you have your mid-sessional next week Friday. And obviously, you know, similar things will reappear. But it's important that I just went through this. I don't know, but I hope, you know, some clarity has been provided with some of the things. All right. On Monday, we'll go through a few questions on transients. Okay. On Wednesday, however, although we have gone ahead of time, or we have ahead of schedule, I'm going to start the next topic on Wednesday, so that we won't be in a rush at the end. All right. So let me just take the register. It is now 6:56. Sir Adams.
Present, sir.
Bert.
Here, sir.
Blackwood.
Present, sir.
Brown, Beresford.
Here, sir.
Busu. Teran. Done. Campbell.
Yes, sir.
Miss Chen.
Yes, sir.
So it's also exasperated. Clark.
Alright.
Marcelo.
Yes, sir. I'm here, sir.
Crossdale.
Present, sir.
Darby. All right. Davis.
Present, sir.
Dona. Just lift this. Ellis.
Present, sir.
Ferran.
Yes, sir.
So Forrester, you pull over. Are you driving again? Forrester?
Here, sir.
So you get the notes, Mr. Forrester?
Sir, I have some friends who will give me some of them notes, sir.
Oh, okay. Grant?
Yes, sir.
Gray?
Here, sir.
Jeffrey?
Yes, sir.
Johnson Antonio?
Here, sir.
Johnson Kenyatta? Okay. Kamika?
Here, sir.
Louis Nicholas? Miss Lynch is still with us?
Yes, sir.
McFarlane?
Yes, sir.
Merritt?
Yes, sir.
Montague?
Here, sir.
Nevers?
Yeah.
Phillips? Still with us?
Here, sir.
Again?
I'm here.
Oh, okay. Porter? Ramsey? Ready? Thomas Manoy?
Here, sir.
Watson? Oh, okay. So Wilson, you stayed with us?
Yes, sir. Yes, sir. I stayed.
Oh, okay.
Yes, sir.
All right. That's it. Have a good evening.
Question, sir.
Somebody say they had a question?
Yes, sir.
Uh-huh.
I know it's a bit of a long shot, but is there any possibility of a makeup test?
You don't need that, man. You have four more pieces of assessment too. You have four more pieces, man. You have the mid-sessional, then you have test 2, and then you have the final exam. The first test was just 15%. All right?
Yes, sir.
All right.
Sir, the assessment that was sent, I message you on it.
The others can sign out. Let me just talk to Mr. Granson.